Welcome to Homework Lib.
So if we look at equation 30.14 of our textbook, we'll see that during charging, the current I changes as epsilon over R, where epsilon is basically the EMF voltage, R is the resistance, then 1 minus e to the power negative R over L divided by T, where R over L times T, where L is the inductance of the circuit. So for part A, we need to find out the initial rate of increase of current in the circuit. So the rate of increase of current can be written as di over dt, and since it's initial, that means time will be at t equal to 0. So if we take the derivative of I with respect to t, we get this following expression. So we have epsilon over L times e to the power 0 at t equals to 0, which is epsilon over L, which is equal to 6 divided by 2.5. So we have 6 volts and 2.5 Henry. So that gives us 2.4 amperes per second. Now in part B, we have to find out the rate of increase of current at the instant when current is 0.5 ampere. So for that case, we have to do the same thing. So we figure out di over dt at time I equals to 0.5 ampere. So di over dt is basically epsilon over L e to the power negative R over L times t, which is equal to, so from this expression, this is equal to epsilon over L times 1 minus R times I at a certain time divided by epsilon. So the way we get that is we are just writing e to the power negative R by L times t in terms of the other terms, which will give us 1 minus R times I at some time t divided by epsilon. So we just replace that. Now using the given numbers, we see that this is equal to 6 volts by 2.5 Henry times 1 minus R, which is 8 ohms. The current is 0.5 ampere, and we divide that by the EMF voltage, which is 6 volts. So combining this, we get 0.8 ampere per second. Now in part C, we have to do the same calculation, but now for current 0.25, and also the circuit is closed this time. So we'll be just using I at 0.255. So we're just figuring out the current when the circuit is closed. So epsilon is now 6 volts divided by R, which is 8 ohms. Then we multiply that by 1 minus e to the power negative R over L, which is 8 ohms by 2.5 Henry times the time, which is 0.255 25 seconds. So there will be a second there, right? So if we do so, we'll have the current as 0.413. So this will be I at 0.25 second. Finally, for part D, we have to figure out the final steady state current. So for steady state current, di over dt will be 0. That means there will not be any change in current. That's when we get the steady state. So if we use that expression for this equation over here, we get I max or I steady state, which is equal to epsilon over R, where epsilon is 6 volts and R is 8 ohms. So combining this, we get 0.75 ampere. Thanks for watching. I'll see you